Okay, we're recording. Thanks y'all for coming, braving the storm to get here. Of course, for those who are arriving late and will be arriving late later, no problem. This is all being recorded. You can watch it later. Of course, we'll redo attendance again after it's over. Okay, so we started last time on parametrized surfaces, and let me just kind of hit the highlights and remind you again of what we were talking about. The idea of a parametric surface is that it's an analog to the idea of a parametric curve. Parametric curve is where you have position as a function of one parameter, and here we're going to have position as a function of two parameters. Right? So now, when you do a parametric curve, you expect it to be one-dimensional, namely a curve, because there's one parameter. In some sense, there's a one-dimensional thing that's going into this function, and so, of course, you get a one-dimensional thing out, or would expect anyway. And so, likewise here with two input parameters, it's like there's a two-dimensional space. There's the whole ST plane is going into the function, and so you should expect to get a two-dimensional, namely a surface output. Just as an easy example of this, I should say a familiar example of this, we look at the parametric plane, right? And this is an idea we talked about back in section 1.5 long ago, but the idea is that if you have a point on a plane, which of course you can think of as a vector, if you like. And if you have a couple of vectors parallel to the plane, if you interpret those vectors as, hey, I can go as far as I want in this direction, because it's parallel to the plane, and I can go as far as I want in that direction, it's parallel to the plane, then we can just look literally at what happens when from my starting point I go an arbitrary amount in the direction of V1, and then from there, an arbitrary amount in the direction of V2, and that will get me all together then, so keeping in mind, we've got our starting point x naught, and then we're adding, going some arbitrary amount in the V1 direction, and then some arbitrary amount in the V2 direction. All together, that gets us to a point which will still always be on the plane, and furthermore, as s and t vary, right? Different s, well, that just pushes you more in this direction, and different t, well, that just pushes you more in that direction. Negative value of s pushes you back this way, etc. Just by making the appropriate choices of s and t, you can trace out the entire plane. Okay? Is that satisfying for everybody? So our parameters then are S and T, and given that there are two such variables, right, then we have 2 degrees of freedom in how we move across the plane, which produces, as expected, a two-dimensional plane. Okay, all right. So, we already talked about this last time, but we have two parameters. So our old crutch from parametric curves, thinking of the parameter as being time. I shouldn't call it a crutch. That's got a negative hinge to it, right? It's perfectly fine to think of parametric curve as being a function of time. But that convenience, right, of thinking of the parameter as being time, you kind of have to jettison that for parametric surfaces, because you got two of them, they can't both be time. That'd be a weird sci-fi movie that that's not, I don't know what that means. Okay. All right. So we talked about the graph parameterization last time. This is a really nice tool for creating a parameterization. In other words, if you know a surface, by some means or another, and you want to figure out, I need a function that parameterizes it. I need to be able to trace out this surface with a function. Here's how you do it if your surface is known as a graph. Right? If it's a graph. Whatever the input variables are, let those be your parameters. That's most of the trick right there. In some sense, once you make that choice, input variables being your parameters, it has already succeeded. We just have to kind of observe and write it down that, in fact, we have already won the game. Because here you go, x and y are functions of s and t. And this formula The fact of it being a graph, the fact of z being a function of x and y, unavoidably forces me to have z also as the expected, the corresponding function of s and t. And lo and behold, we have a parameterization because we have position as a function of two parameters. All right, everybody see how that works? Clever trick. Wish I'd thought of it. Somebody showed this to me many years ago. Neat trick. Nothing magic, by the way, about z being the variable that has been solved for. So this was our last example last time. Suppose y is a function of x and z. No sweat. Same trick works. You might even not have it already solved for. You might have to solve for it. Fine, whatever. That's, a little preliminary effort. But once you have one of the variables as a function of the others, right? So x and z are our input variables. We let them be the parameters. And then our hands are tied. We've already won the game, whether we like it or not. So, y kind of has to be this, and we're done. We have position as a function of two variables, s and t. Okay. How are we doing? Is everybody happy? All right. So what if you're looking not at a rectangular graph, but what if you're looking at a graph in a different coordinate system? So, for example, a spherical graph. And let's look at this equation right here. This is what I call a spherical graph, because one of the spherical variables is a function of the others. Here we have rho as a function of phi and theta, instead of z as a function of x and y. Right? So let's call that a spherical graph. Roughly the same trick works. The only difference is you've got to kind of start from your conversion formula. So you do have to kind of write this down first, because whenever you say a parameterization, the implication is that we're talking ultimately about position, namely rectangular position, as a function of your parameters. So we're going to start by saying, we want rectangular. Okay, but now that we're in the language of spherical coordinates, having written this down, same deal, pretty much. So this formula kind of forces us to do this, right? And I didn't even have to let my input variables be parameters. They're already not x, y, and z. I mean, I guess I could call phi, call that s, and theta, call that t. If you really want to, I suppose you could. But in some sense, the only purpose of that is to avoid the issue of, for example, if I were to just let that be x and let this be y, then I would have x and y being both input variables and output variables at the same time. And that gives me the willies. It's not that anyways, some people will do that, and I'm perfectly comfortable with what they mean when they do, but I do still think it's a little cringy. Not even necessary here, because again, we're looking at our outputs actually being x, y, and z. So just leave phi and theta as phi and theta, and we win already. Right? So what this boils down to is when you have a spherical graph, just plug that into the conversion formulas. Boom! Parameterization. Everybody happy? Okay. All right. So that is a great trick. The graph parameterization. This is my desert island. If I could only have one parameterization method, you got to pick that. I think I'd have to pick this one. Okay. All right. So now here's some other tools, and as you all know, you can't sort of memorize algorithms to suit every particular circumstance, right? You should think in terms of having a toolbox full of tools, try to make sure you develop and understand the tools, and then use the tools appropriate to the situation at hand as it comes up. Because who knows, life is full of too many different kind of circumstances. We can't categorize all of them. So here's another tool for your toolbox. you can use vectors in some nice ways. Now, we saw some examples of this with parametric curves. Y'all may recall the bicycle kind of rolling down the street and the reflector and what's the motion of the reflector. And, it's much easier to handle with a little bit of vector algebra. So here's a weird example, but where, again, we're going to use vectors to great effect. Suppose I have a surface like this, and then at every point on this surface, what we're going to do is we're going to look perpendicular to the surface, and we're going to go a distance of 1 in that perpendicular direction, and that will give us then a point on a new surface. As you do this for every point on the purple surface, you get a new sort of larger, if you will, orange surface there. Everybody see what I'm talking about? Okay, so how do we parameterize the orange surface is the question. All right, and I find it amusing to think about this as being someone's head, and this is their hair standing on end. Right, somebody said something scary. And then the question is, what does that make their head look like? Right? All together, their hair looks like it's like a hat or something. Okay. All right. So what I'm going to do is observe that pretty much the point here is that this point plus this vector gives me that point. Right? So I can think of the surface that I'm actually interested in here. This the outer part of the hair surface, if you will, as being, well, it's a sum of two vectors. There's a vector describing this purple point on the surface, and then there's a vector describing the moving direction, in the perpendicular direction by distance 1. So I'm going to understand the dark blue point by just writing down a formula for purple and a formula for orange and adding them up. Right. So here we go. The purple point, well, that's on this surface. That surface is a graph, and so I'm going to use the graph parameterization. Right. So writing down a formula for the purple point is old news. Everybody with me so far? Okay. All right. Okay. What about the orange, though? What do I do with the orange? Well, here's the thing. I've got to think this through carefully. This surface is a graph. True. There it is. It's a graph. It is also a level set, though, because again, keep in mind we have fishing through our toolbox. Oh yeah, I forgot about this old tool from chapter. I guess it was early chapter 2. Anytime you have a graph, you can rewrite that graph as being a level set of a different function. And now, do notice I did have to fiddle with the algebra. Right here, as written, this is a graph. It's a graph of this function 4 minus x squared minus y squared. It is not a level set of 4 minus x squared minus y squared. You got to move the algebra around. Legal, reversible algebra to get down to this thing equals 0. And now you've got, we're literally looking at a level set of this other function. Everybody happy with that? If you're maybe a little, rusty on what the deal was with graphs and level sets and all that stuff, look back through the early chapter 2 discussions. Okay, so point being then that this surface that we're interested in here, and I'm going to, I guess I'll call it purple. That's fine. So we're going to view this as being a level set of that function. I like being able to view surfaces as level sets because we have, again, various tools that we can use. Once you know that it's a level set, you can make observations like, that means then the gradient is perpendicular to that surface. Right? Gradients are perpendicular to level sets. So all I got to do is take the gradient here, the gradient of this g function is going to be perpendicular. And that's easy to write down. There you go. How are we doing so far? Okay, now real quick, don't forget we've already agreed that from our purple parameterization that x and y are going to be s and t, and so that turns that into that. Okay. All right. So the only little tweak I've got to do to this now, though, is and again, looking at the picture, I see that I don't actually want the gradient itself. The gradient is just kind of a means to an end. It's a way of identifying the direction perpendicular to the surface. What I actually have, the actual hairs standing on this person's head are of length 1. And so I need to find, to get this normal vector, I have to normalize the gradient. So we divide the gradient by its own length, and we get that. So yeah, you see here we're taking the gradient, dividing by its magnitude, and that gives us this n vector. So we've got the purple point as a function. Oh, whoops! I did the wrong colors there. Sorry. Let me do that again. I've got the purple point as a function of s and t. I've got the orange vector as a function of s and t. And so all together then, keep in mind what we actually wanted was, I erased. Yeah. So I have the purple, I have the orange. What we actually wanted was this point over here defining the surface we actually care about. I need that as a function of s and t, and purple, dark blue, I guess you would say, then is just purple plus orange. As planned in the first place. Everybody happy with that? So it's otherwise very hard problem, right? I mean, if you think about it, this shape here, if depending on how long the hair is, right, it would approach spherical in the limit. So this dark blue surface is not a paraboloid, right? It's it's some different shape, but it's definitely not quite a paraboloid. It'd be hard to. I don't know how else I would go about even figuring out. Can I view this dark blue surface as being a graph of something? I mean, in theory, it passes the vertical line. I don't know how I would go about figuring out what that function is whose graph we're looking at. But parameterizing with vectors works out nicely. Okay, yes?
When did we learn that the gradient would be perpendicular to both of those?
Yeah, so that was in section 2 point something. It was late chapter 2. There's a section called directional derivatives, or maybe it's called directional derivatives and gradient, and it's in there. Yeah. So yeah, again, long ago. Here we are in chapter 7. Chapter 2 was a long time ago. Yeah. Okay. Alrighty. So welcome all that have been coming in. By the way, I'm totally understand that the tornado warning and all that. So no problem. And we'll do attendance after class is over. Okay, here's another tool for your toolbox. Sometimes you're not looking at a graph, and it's also not clear how just vectors alone would help you solve the problem. And so let's consider, for example, this torus. And by the way, if you're not familiar with the idea of a torus, it's what you get when you rotate a circle around an axis contained in the same plane that the circle is. So it's a donut, right? It's everybody knows donuts. Okay, surface of a donut. How would we parameterize this torus? So here's the different tool for your toolbox. I like to think of this, and this is just my point of view, but make up a coordinate system, and then once you have a coordinate system set up, use other tools in your toolbox to take it from there. Right? So here's the for example concerning the torus. If I were going to create a coordinate system on the surface of the torus, right? On that torus, how would I describe where we are? Imagine this was a weird shaped planet, and how would you describe your location on that planet? I think a reasonable choice would be to talk about, okay, well, we're going to have a kind of an equator of sorts here, if you will. And we could talk about what is the angle, what is this angle T from the center of the donut, right? The center of the center of the doughy part of the donut, not over here, right? From the center of the handle, if you will. What is the angle that you would have to go, what you might call north, from the equator to get to level with where you actually are, right? So that's what you might call that latitude, right? This green angle you might call latitude. And then there's the analog of longitude, which would be, all right, how far from there do you have to rotate? What is this angle here by which you'd have to rotate to get to where you actually are, right? So your actual location there is going to be some amount, the usual, counterclockwise around the z-axis. How far from the what you might call the prime meridian, right? How far do you have to go east to get to where you are? So it's longitude and latitude, basically, right? So we've got these two angles. We've got this. Let's see here. Got this green angle and we've got this red angle, and I just made it up. Right? Wasn't given in the statement of the question or anything. How we doing? Is everybody on board? If we lived life on this planet, I think that'd be a pretty reasonable way to describe where you are on the surface of that weird planet. Okay, so with that done, now we can start writing stuff down. Now again, we're going to be using other tools to do this, but let's talk first about, let's see here, let's talk about this point here. Which, to keep my picture simple, I'm going to kind of redraw it over here. How would I describe where that point is? And no problem, I can describe that point by observing innocently that, it's this vector, which is easy to write down. Right, that distance is given to be a, and this is this vector, this blue vector, is in the x direction. So, boom, right. And then, now here's where it's a little trickier though. I need to add this vector, and that's not constant. That vector is clearly going to depend on the angle. It's going to depend on our angle T, right? This sorry, my arm. This is going to depend on that angle T. And it depends on that angle T like so. What do you think? Everybody see that? So for different values of T, it's going to be kind of going around like that. In some sense, as a function of T, we're kind of tracing out a circle in the XZ plane. And so cosine and sine in the X and Z coordinates. Magnitude of B, because the radius of the handle of the donut, if you will, is given to be B. Okay, so we had to use some vector algebra there to figure out where this P point is. And now once you have P, all right, let's see here. Hang on. Orange. Okay, so now that you have P, how am I going to get the point I'm actually interested in? Okay, so we know this, we know P, but my actual location is there. I am some distance east of that P point. And so, well, here's the thing, I'm just gonna rotate, I'm just gonna observe that if you just rotate by this angle, that angle being S, right? Rotate by that angle S, and that takes the P point that we already have formulas for to the X point describing our actual location. So it's a different tool from our toolbox. It's not, we're not doing sort of, breaking location down as a sum of vectors here. I'm using a different tool. Hey, this is a rotation of that. And this rotation is an old linear algebra problem. And recall, one of the things we talked about early in the class, you got to make sure you're really good with, especially this specific part of linear algebra, of understanding that things like rotations and reflections, that kind of stuff, and there's of course many other examples, are linear transformations. Linear transformations are represented by matrices. Matrices are understood by their columns, and those columns specifically are the images of the standard basis vectors. And so what you'd have to do to think this through is think about, all right, what happens to the standard basis vectors as you rotate by an angle S counterclockwise around the z-axis as seen from above? Right? What does that do to the standard basis vectors? And that will give you the columns, and that gives you the matrix. Y'all think you can do that? Is that okay? It's a good exercise, I'll say, to make sure you can think that through. And I'll say this: this is be a great topic for office hours. Perfectly fine for the help room. And let me know if you have questions about filling in those details. Okay. All right. So it's all over at this point. We know the coordinates of the of this orange point. The orange point is P. I need to rotate it by this matrix R over here. And there it is. Here is literally, I am rotating P previously computed. And you multiply out that algebra, and there you go. We win. Location on planet Donut is given by this formula, depending on S and T. Namely, again, a reminder, that's like longitude and latitude on the donut. Okay. Now, the particulars of this example, the actual particulars of the rotation and the vector addition and all that stuff, that's all specific to this example. Of course, make sure that you can do that. Those also are tools that I expect you to have in your toolbox. The big picture here, though, the new idea is that our foot in the door, the thing that allowed us to kind of get going on this, is that we created a coordinate system. Right? We created a coordinate system, this longitude and latitude business, and then from there it was sort of details. But there's many other circumstances where the thing you're looking at, if you just, how would you keep track of your location? Just ask yourself, what would be the most convenient way to describe with two coordinates where I am on this thing, right? And that gives you a coordinate system, and then you can do geometry and algebra from there. Okay. All right. Okay. Last one I'm going to show you. Sometimes you have an existing parameterization that's not exactly what you want, but maybe is close in a way, right? And you can deform that existing parameterization that's close to what you want, deform it to become what you actually want. Okay, all right. So starting with this, here's an existing parameterization of the unit sphere. By the way, where did I get this from? This is a spherical graph parameterization. Right, it's a neat trick to observe. Now, most people like to think in terms of rectangular coordinates, but this is not a graph in rectangular coordinates, but it is a graph in spherical coordinates. And then if you just, in the usual way, plug in rho equals 1 into our usual conversion formulas from from spherical to rectangular, and bam, we have ourselves a parameterization of the unit sphere. How are we doing on this part? Everybody good? Okay, well, here's the thing. Suppose you wanted to, and by the way, I can recopy that sort of, if you will, vector form of the parameterization. I can write that down separately as 3 separate equations, I suppose, if you want. Okay. All right. So, what, though, if you are interested in an ellipsoid, not a sphere, an ellipsoid, like so? Well, there's a couple different ways you can think about this. The first observation I'm going to make is that there is a deformation happening, right? I have a sphere, I want an ellipsoid, and the process for turning a sphere into an ellipsoid is to stretch it by different amounts in different directions, right? And so the stretching, you can see this in a couple different ways. How much did I stretch this, to get, how much did I stretch this to get this? Well, you can see I stretched by a factor of A in the x direction, factor of B in the y direction, C in the z direction, and you can tweak the parameterization kind of either of 2 possible ways. You could start with your sphere. Green is our parameterization of our sphere, and you can then just straight up literally just stretch x by a factor of A. This says I'm going to make my x coordinates A times as big. And then likewise B for y and C for z. So there I'm just sticking the stretchings right into the formulas for x, y, and z. So that's one option. And notice that does give you a parameterization of your ellipsoid. And furthermore, you can check this by popping in for x, y, and z and confirming that equation works. Not too much trouble. Good exercise. Okay, here's a different way you can think of, different way you can think about it. I guess I did want to leave that. Different way you can think about it is think of it as that this, get rid of this, this is your sphere, looking at it sort of in terms of a bunch of equations, and now we just ask ourselves, how do I stretch things out if they're described by equations? And we have this rule that, and you can see it in action right here. Everywhere you had an x, you replace it with x over a, etc. Right? So I can do that here. I can replace this x with x over a. And likewise for the y and the z. And that gives me this set of equations, right? So I've turned the green equations into the blue equations by doing kind of a chapter 2 version of the stretching. Replace x with x over a. Y with y over b, z with z over c. And notice, conveniently, even though we're taking this different point of view, we get the same parameterization. Right? If you were to solve for x, y, and z in these equations, you would get exactly this parameterization. Okay, so take your pick on which point of view you like better. I think it's best to understand both of those points of view, right? Because you never know which one's going to be the more convenient in the circumstance you're looking at. Either one of these points of view allows you to turn an easy parameterization into a harder parameterization. Okay. Pausing. Questions? Yeah.
So to use this, we'd still plug in like the A side equals theta.
Oh, yeah. So parameterization means position. So position remains x, y, z, right? This needs to be functions of other things, and so the A, B, and C you kind of have to go over the other side to make them actually functions. Yeah, I just left it in this form so it'd be easier to see that I've literally replaced x with x over a. That's all that was. Yeah, right. Okay. Anybody else? Good. All right. I've already made this comment. Let me just remind you, there are a bunch of examples in the book. I feel it necessary to point out that they are all sort of the opposite of the examples that I've shown you. I've shown you how to create parameterizations from other knowledge of the surface. The book shows you how to figure out other knowledge of the surface from an existing given parameterization. So that's still good stuff. And in fact, by the way, the torus example is in the book, right? But what they don't give is information on how to create the parameterization of the torus. So, anyway, still good examples in the book, and I hope you'll take a look at them. All right, so now on to using parametric surfaces to understand a new kind of an integral, and we're going to have to work our way up to it by developing several ideas, so bear with me here. All right, so parametric surface. I'm going to make a silly observation, a seemingly silly observation, that if you have two variables, right, but then if you fix one of the variables to be a constant, well, now you have one variable. Just like I say, it's kind of a silly observation. If you have two variables, but one of the variables isn't a variable, then you have one variable. Tautological, you might say, observation. So, so what I've got then now is I've got position, x, y, z, as a function of, well, just the one variable now. And if you've got position as a function of just one variable, right? Position as a function of only one variable. Well, we know what that is. That's a parametric curve. That's the definition of a parametric curve. Right? And likewise, I mean, I didn't have to fix only t. If I had fixed s, well, now I've got position as a function of t, but again, namely only one variable, and again, curve. Okay, so these are what we call the coordinate curves of the surface parameterization. So a nice example here, I like the sphere. So let's talk about the theta coordinate curve. The theta coordinate curve is what you get where you fix a value for phi. So phi is not allowed to change. Phi is now stuck at being that angle like that. No changing for phi. And with that said, phi being fixed, that means that all of this is constant, and that's constant, and that's constant. And if I ask, well, what happens now? How is position a function of theta? As theta changes, as I move along in the theta direction, with, again, phi fixed. Well, then I just move along like that on the surface of the sphere. You might say I move along that latitude line of the sphere. Does that make sense to everybody? Okay. And then likewise, if you go the other direction, let's just for the sake of completeness, what happens if you fix theta? Right, so now theta is not allowed to change. Now this is a constant and that's a constant. And with theta fixed as, let's see, I better draw that in this picture here. Theta is fixed at that value. Then, well, moving in the phi direction, right, moving in the phi direction like that. Okay, well, phi is allowed to change. All right, well, then we're just going to be kind of moving down that meridian, that longitude line, if you will, on the surface of the sphere. How are we doing? Yep.
Why do you know it's down?
Oh, just because as phi increases, I mean, phi equals 0 is straight up, right? And then as phi increases, that's the way it goes. Yeah. Okay. Yes.
Are these directional curves? Like, does it matter that it's going down, or?
Yeah, I mean, because at some point momentarily we are going to talk about the velocity, and so the velocity does depend on which direction you're going. So yeah, totally. It's a good question. Yeah. Right. Okay. All right. So now let's ask the question. What can I say about the derivatives of this function? And I think this is a reasonable thing to want to ask. And it turns out we're kind of already there. But if I talk about the partial derivatives, just to ask a question, what is a partial derivative of the parameterization? I'm just going to, working off of this picture. Well, a partial derivative says, and let's do the partial with respect to theta, let's just say. Partial with respect to theta says that I'm going to fix phi as being a constant, right? Treat correspondingly everything that is only a function of phi as a constant. And then I'm going to take the derivative with the single variable derivative with respect to the only remaining variable. Well, gosh, that's awfully familiar, right? This process of taking a partial derivative of x is exactly the process of writing down the theta coordinate curve and, just take the derivative of the theta coordinate curve. And, side note, the derivative of a coordinate curve is the velocity. Right? So a partial derivative of x is a velocity vector of a coordinate curve. Does that all sound good? Yeah. Okay. All right, and likewise in the other direction. So that allows me to talk about position differentials. So, let's imagine hypothetically that I'm at this point here in phi theta space that has me at some corresponding spot on the sphere. And suppose I were to move by some amount in the theta direction. Right? So suppose, phi is constant, right? Moving only in the theta direction. Phi constant, I move by some differential amount in the theta direction. How far do I move on the surface of the sphere? And, I know what the velocity of this vector is, of this parameterization. We know what the velocity is. Velocity is just a partial derivative of that parametric curve. And so I can compute the corresponding differential of position as, this thing here is just velocity times time, right? It's, I say time, differential of the parameter. So we've got a velocity telling you how fast you're moving in that direction per unit change of theta. I know what my change of theta is, and so multiplying tells me what the actual change in position is. So x theta d theta is that vector. And then analogously, if I were to move in the phi direction by some amount, then I'm moving. I know the velocity of the phi coordinate curve, and that velocity times d phi gives me my phi position differential. Yeah. Everybody all right with that? So I like to start off with the example here of being able to see an actual, right, relatable, concrete example, and then just to point out in general. Let's see. And I have it right here. In general, if you're talking about not phi and theta, but if you're talking about s and t, then these are the formulas for your position differentials: xs ds, xt dt. Okay. All right. Well, we are in good shape to actually do some surface integrals now, because look at what we've got. We've got this surface over here, this dimensionally awkward thing. It's two-dimensional in terms of it itself. There's two coordinates to describe where I am on it. It's a two-dimensional thing. The surface itself doesn't have a volume. The inside has a volume, but the surface itself doesn't have thickness. It doesn't have volume. But I've also got it viewed as being a function of two parameters. And so in the same way that we did pullbacks through the parameterization with parametric curves, right? If you have a parametric curve, everything on the curve, you pull back through the parameterization to write in terms of your curve parameter. Likewise here, things that I need to understand on this sphere, I'm going to pull back through the parameterization to understand in terms of phi and theta. Does that make sense to everybody? Okay. All right. Now, of course, to do that, I need to know what my stretching factor is. So I need to know how much area there is in that little piece of surface. And area is computed by this old formula here. It's the magnitude of the cross product of the edge vectors. These edge vectors we just got through computing on the previous page. Right? Those edge vectors are x phi d phi and x theta d theta. So magnitude of their cross product. Notice we can pull out scalar factors. Right? So d phi, missed. D phi pulls right out, d theta pulls right out, and lo and behold, we've got then that blue area as a multiple of that green area. Right, I've got area on the sphere as a stretched out factor multiple of area in phi theta space. And that stretched out multiple is this is our stretching factor. Let's see here, I'll do this in orange, I guess. There's our surface, let's see how to say this, parametric surface stretching factor. Anybody follow? For whatever it's worth, notice that this is kind of a rip-off of what we did with change variables, right? We drew some vectors, computed an area, and then asked ourselves, well, how do I compute that area, and how does it relate to this other thing? The geometry is different. Here we're looking at a parallelogram in space instead of a parallelogram in the plane, and that's why we get a cross product instead of a determinant. It's because, this parallelogram's in 3 space. Each vector's got 3 coordinates. It's just a different algebra and a different geometry. So we can apply the correspondingly different formula, and we get cross products instead of determinants. So flashbacks to chapter 1 there. All right. Okay. So, with that done, I'm going to point out that this vector here on the inside, the thing whose magnitude is the stretching factor. Turns out this vector is going to be interesting. It's going to be useful in a lot of ways. So I'm going to give it a name and a notation. I'm going to call this the parameterized normal vector. The book gives it a different name. The book calls it the standard normal vector. I mean, look, it's just terminology. I guess that doesn't matter. But to me, to my ears, when you say standard, that makes it sound like there's something canonical or something natural or intrinsic about it, and there really isn't here. I think it's very important to note this capital N vector is not really intrinsic to the surface. It's part of the parameterization. The parameterization is what creates it. And there's lots of different ways that you can parameterize a sphere. Right? So depending on the whatever parameterization you might happen to pick, or whatever your surface is, you're going to get a different value. You're going to get a different vector. This capital N will be different every time. Can they all be standard? I don't know. To me, that just doesn't. The word standard doesn't track for me. I'm uncomfortable with it. So I call it the parameterized normal vector because it depends on the parameterization, as it should. I hope that makes sense. Y'all happy with that? Yeah. All right. Okie dokie. So, by the way, another neat thing about this, don't forget that these vectors here are tangent vectors because, well, they're tangent to the coordinate curves. The coordinate curves are inside the surface, so these are tangent to the surface, and therefore their cross product. Let's see here. Their cross product, namely this capital N. That capital N is always going to be orthogonal to the surface, otherwise known as normal to the surface, which is why we use the letter N in the choice for its name. Okay, is everybody doing all right? All right. Okay, so so the stretching factor is magnitude of capital N, and we're out of time, so we will draw the line right here and pick up, hopefully with better weather on Monday. Y'all have a good weekend. Try to stay dry today, and have a good one. Oh, and of course, stick around for attendance.